All right, what's up, everyone? You all ready? You have fun with that homework?
Yeah, it was all right.
No? How about questions? I know I've already helped at least one student with number 6. So what do y'all got? What do y'all got for me here?
Oh yeah, 6 was weird.
No requests?
Could we look over 6 actually?
I don't mind doing 6. It's going to take
Cool.
a little while, but I don't
Yeah.
mind doing it.
Because I remember doing it, and that one was one that had a lot of stuff that I was sitting there looking at afterwards, going like, that just doesn't seem right.
Yeah, yeah, let's go through it now. I will say I'm going to move a little quick, all right, because time is of the essence here. So we're given a function and we're trying to figure out where it goes up, where it goes down, any local max, local mins, where it's concave up, concave down, and where we have any inflection points. This is going to require that we take the first derivative and the second derivative, and then basically find the critical numbers and stuff like that. So I'm going to start by just taking the first derivative. The first derivative of this function, I'm going to have to use chain rule on the cosine squared x. And then I'll take derivative of this separately. So the derivative of cosine squared x is 2 cosine x times the derivative of cosine x, which is negative sine x. And then I can say minus 2 cosine x. And cleaning that up, I can put negative 2 cosine x sine x minus 2 cosine x. So that's my first derivative. Any questions there? Chain rule, good? All right, there's my first. Now I'm going to need the second derivative. I may as well get it now because I'm going to need it. So while I'm taking derivatives, let's go ahead and get the second one. So when I take the second derivative, I have to realize I have a product right there. There's a product on these two. This one I can do separately, but these I have to do as a product rule. So I do derivative of this times this plus derivative of this times this. So when I take derivative of the first one, I'm going to have the negative 2 come for the ride, but then the derivative cosine is negative sine. So that'll change that to a positive 2 sine x. Now times the second one, plus now the derivative of the second one, which is cosine x, times the first function, which is negative 2 cosine x. And now I'm done with the product rule. I still need the derivative of this, which is going to be a positive 2 sine x, because when I take derivative of the cosine, it spits out a negative and it was already being subtracted, so now it becomes a plus. I'm going to clean that up. This is 2 sine squared x minus 2 cosine squared x plus 2 sine x. And just pay attention, that's a negative 2 because that was a negative right there. I sure wish it would have been plus. I sure wish it would have been plus, because if this was a plus, then I'd be able to factor a 2 out of both of those, and then I would have had sine squared x plus cosine squared x, which equals 1 by the Pythagorean identity. But we didn't get that lucky. So that's what it is, okay? All right, so we got our first derivative and we got our second derivative. Now, let's find critical numbers. So that was all kind of like preliminary work. So now what I'm going to do is figure out where the first derivative is 0. I'm going to figure out also where the first derivative does not exist. So when I look at where it's 0, I have to take the function, the actual derivative, negative 2 cosine x sine x minus 2 cosine x, and I have to set this equal to 0. And so if you go back and you remember, well, if you go back and look, I'm sure in one of our first lectures, I said the 2 things that I want students to come to me from pre-cal with is the ability to understand the unit circle and to be able to solve trigonometric equations. Those are the 2 absolute essential ideas that you have to feel good about Cal. Well, there's a lot of other stuff, but those are the 2 things I always say. Know your unit circle, know how to solve trig equations. Well, here we are, we've got a trig equation, right? So the technique here is to first try a GCF, so I can pull negative 2 cosine x out. And if I pull that out of both terms, I'm left with the sine x plus 1 here equals 0. That's just factoring. And then once I have it factored, I can set each factor equal to 0. So -2 cosine x equals 0. And the other equation is sine x plus 1 equals 0. And then on this one, I can just divide both sides by -2. And we'll still have cosine x equals now 0. And then this one, we just move the 1 to the other side, so sine x is -1. Now, you need to tell me between, look at our domain, we have a restriction up here, okay? Between 0 and 2 pi, where is cosine 0 and where is sine -1? That's what you have to ask yourself, right? So I'm gonna go with the unit circle. Let's look at this one first. On the unit circle, cosine always corresponds to the x coordinate on the circle. So this is really saying where on the unit circle, at what angle is the x coordinate 0? So that happens here and here. At pi over 2 and at 3 pi over 2, that's where my x coordinate is 0. That's where cosine is 0. So I will say that my solutions here are pi over 2 and 3 pi over 2. And I'm really happy that the original function was on a closed interval, 0 to 2 pi. Because if it wasn't, I would have an infinite number of solutions, because there's an infinite number of angles where you would get 0 for cosine. But lucky for us, it's a closed interval. All right, so 2 answers there. Now, the other equation, I want to know where sine is -1. Now, sine is the y coordinate. So where's the y coordinate -1? Right down there. And that happens at x equals 3 pi over 2. But we already have 3 pi over 2 from this over here. So we've kind of got it twice. That means we only need to consider one of the answers. We don't have to consider them both. They're the same answer. So far, we have 2 critical numbers so far. Now, where does the derivative not exist? So this means you go to the derivative, you look at it, and in talking with one of your classmates earlier, there was some confusion here. When you're looking at where the derivative doesn't exist, what you can really do is look at the derivative and look at its domain. Are there any problems with the domain of this? Are there any numbers you cannot plug in for x here that would cause a problem?
Not to my knowledge.
Yeah, because sine and cosine are both nice functions, right? I mean, they're defined everywhere. So you should never be able to plug a number in and then get like undefined, right? Type in sine of anything into your calculator, right? Sine of any number and you're going to get an answer. Cosine of any number, you're going to get an answer. So we have no issues here. All right, so we only have 2 critical numbers. So what do we do with those? Draw a number line, right? Now, we do have a domain restriction, right? 0 to 2 pi. So when I'm drawing this, I need to keep in mind I can only go from 0 to 2 pi. And now let me put my critical numbers. Pi over 2, let me see. In the middle is pi. Pi over 2 is halfway. 3 pi over 2 is 3/4 of the way. And this is where my critical numbers are, right? My critical numbers are these 2, right? I don't really need the pi in here. Now what I do is I pick test points. So I need to pick something here, something between these 2. So pi is a really good one. And then something over here. So what I would do to pick these is just think about the unit circle, right? Our critical numbers are here and here, right? Pi over 2 and 3 pi over 2. So when we're looking between 0 and pi over 2, we can pick any angle we want over here. So a nice, really convenient one would be here, right? Like pi over 4. That's a good test point. And then between this dot and this dot over here, I can pick any angle I want. So why don't we pick this one right here? So that would be pi, right? And then I need something between here and here and 2 pi. I have to stop at 2 pi. So something over there. What? 7 pi over 4?
Yeah, 7 pi over 4 is good.
Seems like a good one. So yeah, you need to know the angles on the unit circle, right? You need to know the common angles. All right, now what do we do with these? We got these tests, we got the test points. we are going to take those and plug those into
Our first derivative.
our derivative, because that'll tell us what the derivative being positive tells us where we go up, derivative negative tells us where we're going down. So I want to know what the derivative is doing. So I'm going to take those numbers, plug them into the derivative. Any questions up to this point? Now, no?
Could you use 0 and 2 pi since they're technically included in the domain, I think?
You could have used 0 and 2 pi. Okay, the only thing I would say on that is just to be careful, because you got to make sure that 0 and 2 pi don't correspond to a critical number, because our critical numbers were here, here, and here, right? If 0 and 2 pi were also where we had critical numbers, then of course you couldn't plug those in. That would be just be careful. That would be the only thing I say. All right. Now we got to plug this into the derivative, right? And here was our derivative. Let me go grab it. We have options on how to plug this in. All right. We got to take pi over 4 and plug it in here. Now you could get your calculator out and do, now if you're in radian mode, you have to do pi over 4. If you go to degree mode, then you're going to convert pi over 4 into 45 degrees, and then pi into 180 degrees, and then this into, what is that, 315? Okay, you could do that, type away, right, and get your answer. All we care about is whether or not it's positive or negative, right? That's all we care about. So I'm going to do something a little different that I think is in your best interest to think of it this way, all right? I'm going to go back to this, and before I plug anything in, I'm going to factor it, just like we did when we were setting it equal to 0, right? Remember, we set it equal to 0, we factored it. I pulled out a -2 cosine x. I was left with a sine x plus 1. Now, I'm not setting it equal to 0, I'm just factoring it, okay? So the top one is just the derivative, the second one is the derivative, but factored. The reason I'm going to look at this one is because I have multiplication here. And so if I know what the sign of this is and the sign of this is, then I know when I multiply them together whether or not I'll get positives or negatives. So watch what happens. I'm going to figure out what's happening. Let's look at what's happening at pi over 4. So imagine that you plug pi over 4 into this cosine, right? Pi over 4. So we're at pi over 4. This is the angle, right? This is pi over 4. Cosine is the x coordinate, right? Cosine is the x coordinate. Now, I know a lot of you know that it's square root of 2 over 2. That's great. That's fine. But all I want you to think about is that it's positive, right? And that tells you that you have -2 times a positive number, right? Now, this is, well, let me put it up here. We have -2 times some positive number. And then we're going to do sine x plus 1. But we're doing, again, pi over 4 in for x. When you're at pi over 4, sine is the y coordinate, which again is a positive number, isn't it? So you know you have a positive number plus 1, which should be positive still. So you have a negative times a positive times a positive. So you know that your answer is going to be negative. Do you follow that, everyone? If you do this, you'll get your negative number, okay? But this to me is just, it's more efficient. To me, it is. And you know, as you move on, you want to be able to analyze things this way as opposed to needing to sit there and chug it out on the calculator. All right, let's do the same thing for pi. So now we're at this angle, right? And we actually know over here that the x coordinate is negative and the y coordinate is actually 0 here, right? I mean, we know it's -1. I understand, we know it's -1, but what's most important is the sign. So if I plug in pi, I'm going to get -2, and then cosine of pi, right, would give you a negative number. And then what would the sine of pi plus 1 get you?
1.
1, right? Because sine of pi would be 0, and then you add 1, you should get a positive number there, 1. Negative times a negative times a positive.
It's positive, yeah.
Right? Making sense? 7 pi over 4 is our last one. Come down here. Oh, yeah, down here. This is our 7 pi over 4. Here's what I can tell you. The x coordinate is positive, the y is negative. Because I'm in the fourth quadrant. To get to this point, I have to go to the right and down. So x coordinate is positive, y coordinate is negative. All right, let's see what happens. We'll have -2 here times, okay, cosine of that angle is the x coordinate, that's positive. And then this part is tricky. This part's tricky. I'm going to do sine of pi, right? I'm sorry, sine of 7 pi over 4. Yes? That should be a negative number. But then I'm adding 1. So if I tell you I have a negative number and I add 1 to it, you actually can't tell me if this is positive or negative, unless you can tell me a little bit more about this number. But what can you tell me? Look at it. I mean, you come down this far, right? That's how far you come down. If you went all the way to the bottom of the circle, that would be -1 as a y coordinate, wouldn't it?
So it has to be less than 1.
Yeah, you know that it's not as, how do we say this? Is it smaller than -1 or bigger than -1?
Its value is lesser than -1.
Yeah, let's say this, it's closer to 0 than -1 is, right? So you know that when you add 1 to this, this should give you a positive number. Because this y coordinate is not quite -1. It's a little smaller. Maybe it's like, well, it's actually -0.707, whatever that is, and then you add 1 to it. So this will be positive. So when you put those together, you get negative. And now we have everything we need to be able to determine if it goes up or down. All right, we're only 18 minutes into the problem. We're not even halfway through. All right, here we go. So this first one here, this tells me that the derivative here is negative, which means the derivative is negative, which means the original function goes down here. And then at pi, the derivative was positive. So the derivative was positive here, which means the original function goes up here. And then at 7 pi over 4, the derivative was negative, which means the original function goes down. So now you can see where it's going up and down, right? And so we should be able to figure out the intervals where it's increasing, intervals where it's decreasing, any local maxes and local mins. Questions? Okay. I'm going to move on. I'm going to let you can do the part where you show, write down the intervals where it's going up and down, local max, local min. I need to get to the next derivative. So let's now do the second derivative, which was right here. And we got to run through everything again. We basically have to take this second derivative. We have to figure out where's the second derivative 0, where's the second derivative not exist. And let's go ahead and just get rid of this now, because when you look at the second derivative, right, there's just sines and cosines again. So there's no issues. But setting it to 0, that's a different story. So again, pre-cal, trigonometric equation, what's the method? Well, in pre-cal, hopefully when you did this, you recognize that this is like a quadratic function. But there's an issue because you've got sine squared and then you've got sine over here, but then you've got a cosine squared. And the cosine squared kind of causes some issues because you would like to have this have all sines or all cosines, one or the other. Also notice there's not a GCF. I could pull a 2 out, right? But other than that, I can't pull anything like a sine or a cosine out. So what I'm going to do is now I'm going to resort to, and this is what you would have done in pre-cal, is you would have gone back to this whole Pythagorean identity. Sine squared x plus cosine squared x equals 1. You would solve it for cosine squared x by subtracting sine squared x on both sides. And then what you'll do is you will replace cosine squared x with this into this equation right here. You're going to replace that in yellow with this. So it'll look like this. 2 sine squared x minus 2 parentheses 1 minus sine squared x plus 2 sine x equals 0. And I guess the whole plan here is to get this in terms of sine and sine, just sine, not sine and cosine. So I'll have to do some more work. I'll distribute a -2 through. So negative or 2 sine squared x minus 2 plus 2 sine squared x plus 2 sine x equals 0. And I have that these two are like terms. So I can put them together into a 4 sine squared x. And then I'm going to put this like in descending order. So I put the thing that had the sine squared first, then the thing that had the sine, and then the number that was by itself. And now what we're looking at is a quadratic. We would say that this is, that right there is what we call a quadratic in sine. It's a quadratic in sine, meaning that the thing that's being squared is a sine function. So this is a quadratic in sine, which means we should hopefully be able to factor this. Now, I know some of you have learned that you can do a u substitution here. You can let u be sine x and then rewrite the entire problem like this. And then go about solving that. That's fine. I'm not going to do that because at the end you have to replace u with sine x at the end. So I'm just going to go right to the factoring. I believe it factors to be, let's see here. You know what I'm going to do? I'm going to kill off a 2. Let's divide everything by 2. They all have 2s. Let's just divide a 2 out. It'll be easier to see it. I'm allowed to do that because I have an equation. I can divide everything by 2 on both sides. So that'll kill off one factor of 2. And now when I factor 2 sine x plus 1 minus 1, that should be the factorization of this quadratic. You can check it. If you FOIL this back out, you should get this. And then we set each of these equal to 0. And then set that to 0, solve for sine x, move the 1 over, divide by 2. Over here, just move the 1 over. And we're finally at a point where we can again go look at the unit circle and see where these things happen. Y'all having fun yet?
Yeah, it's interesting. I really messed this one up when I was doing it in the homework.
Did you mess up the derivative or did you mess up trying to set it equal to 0?
I messed up the second derivative and I messed up all of this unit circle stuff. I completely spaced on all of it.
Okay.
I got technically the right answer on the first one, but I didn't get the second half of the right. Like I got, pi over 2, but I didn't get, 3 pi over 2.
3 pi over 2. Okay.
That was just like I was missing those portions of it. So.
Okay. So now I need to know about my unit circle here. I'm looking for sine. I'm looking for where the sine function is 1/2 and sine is the y coordinate. So I need to be familiar with these points. They are here and here. That's pi over 6 and 5 pi over 6. Those are the 2 places on the unit circle where the y coordinate is 1/2. And then here I need to know where the y coordinate is -1, which happens down here. That means that x has to be 3 pi over 2. All right, number line. 0, 2 pi. We have a restriction, right? Well, where are these things? Here's pi. Okay, so pi over 6 is kind of close to 0. So it's like right here, pi over 6. And you know, let me highlight, these are our critical numbers. Okay, that's our critical number. Then 5 pi over 6, that happens before I get to pi. That's before I get to pi. So a little bit before pi, I've got my 5 pi over 6. That's another critical number. And then 3 pi over 2 is halfway between pi and 2 pi. So that's like right here in the middle. We have 3 pi over 2. And that breaks that up. So those are my 3 critical numbers. And now I need test points. And Josh, let's go with what you suggested earlier. Let's go ahead and to the left of pi over 6, let's pick 0 because it's in the domain of the original function. It's also in the domain of the derivative because the derivative basically there's no problems with the second derivative. There's no issues with it. So I'm going to pick 0 as a test point. I'm going to pick any number between these two. What's a good
Pi over
number?
2 would be a really nice one.
Pi over 2, right? If you look at this between these two dots, straight up would be good. So pi over 2 would be a good test point. I like to circle my test points so that I can distinguish them from my critical numbers. And then between here and here, pi is sitting there, it just wants me to use it, right? And then over here, let's just use the 2 pi. And I'm going to take each of those, all 4 of them, and plug them into the second derivative. And this is going to tell me my concavity, concave up, concave down. That's what it's going to tell me. So I need the second derivative at 0, the second derivative at pi over 2, the second derivative at pi, and then the second derivative at 2 pi. And my second derivative is this, right? That's my second derivative. Now, be careful. You might be looking and saying, oh, look, this is sine squared, this is cosine squared. I know that this is positive. I know that that's positive. The problem is you're subtracting these two. So you can't tell me that, oh, this positive and that positive together is going to be positive or negative. You can't tell because you can't tell how big they are. Right? If I tell you I have a positive number, I'm going to subtract a positive number. Can you tell me whether or not that's positive or negative?
No, not without an idea
Right.
of the magnitude.
That's right. It could be 5 minus 4, or it could be 4 minus 5. You don't know. So unfortunately, we can't work with this. But can't we work with the factored one? Where was the factored one? Yeah, let's go back to this one right here. Because all we did was algebra on it to get it to here, right? Let's go to this one. Right. Now we had pulled a 2 out, didn't we? Remember we divided everything by 2? I'm going to put that 2 back here, okay? So imagine we were at this step right here and we pull a 2 out, and that would put a 2 in front of this, and then break this up into these 2 factors, you'd still have the 2 in front. So let's talk about this. At 0, what happens? So I'm going to just go as quick as I can through this. If I plug into here, since there's a 2 out front, that's always positive. I don't even care about it. What is sine of 0? What's the y coordinate at 0?
It should be 0.
0. Take away 1, negative, right?
Negative
A
1.
negative
Yeah.
number times now sine of 0 again. Sine of 0 is 0 plus 1. Positive number. Those two multiply to be positive. Pi over 2. Question? What?
Shouldn't those multiply to be negative?
Oh yeah, they should be negative. I don't know why I put that. Thank you. Yeah. Yeah, the world is not yet collapsed upon itself. Pi over 2. I got to plug pi over 2 in. Okay, what's sine of pi over 2? So pi over 2, straight up, y coordinate?
1.
1. Okay, so this is 2 times 1 minus 1. 1? So positive?
Yes.
Times, and now here, sine of pi over 2? 1 plus 1 is 2. Get another positive.
Positive.
Yep. Okay. How about pi? So sine of pi, -1?
Should be 0 still.
0, right? We're looking at the y coordinate, right? So go to pi, the y coordinate 0, so that should give you a 0. Take away 1, we got negative.
According to that.
Okay, sine of pi is
0 plus 1.
0 plus 1 is going to be positive.
Positive.
That gives you negative. Hey, they're switching, right? They're switching. Got to check them all. I told you that last class. Check them all. So 2 pi, sine of 2 pi is 0. Minus 1, so you get -1. And then sine of 2 pi is 0 plus 1, you get positive here. Wait a minute, are these both negative? Or is that negative there?
That looks like, yeah, they're both negative.
Oh, it didn't switch, did it?
Interesting.
That didn't switch. That's why you can't just be like, oh, I'll find the first one, just all the others will switch. You got to check them all.
I would
All
say, couldn't we, looking at them, just, I mean, obviously, you know, we're looking at that method real fast, but also looking at those, we should be able to just look at them and know immediately that the 0 and the 2 pi will be the same. Like
For
the
sine,
values,
for sine,
yeah, their
yes.
signs will be the same, you know, because, you know, they're the same output.
Yes, but I'm saying for the sine function, because our second derivative only had the sine function in it, yes.
Yeah,
If
yeah,
it
no,
had the
if we had
cosine
other
in there-
stuff,
Yeah, if cosine was in there, there could be some differences. Because then cosine at 2 pi and pi are different. Were you saying 2 pi?
Oh,
Were you saying
2 pi
or
and 0.
Oh, yeah, 0 and 2
Yeah.
pi, you could say yes, same answers.
Yeah,
Exactly, because they're coterminal angles. All right, so we're here. What does this all mean? It means that the second derivative is negative here, which means the original function is concave up here. And then the second derivative here is positive, which means the original function is, why did I put concave up? That should be concave down on that first one. Concave down, right? Negatives, second derivative, negative people frown, concave down, right? Second derivative, positive people smile, concave up. At pi, we should be down, concave down, and then concave up.
shouldn't it be concave down again?
Down, sorry. So F is going concave
You
down.
made me worried for a minute there. I was like, oh God, did I do that backward on all of the homework?
Yeah, no, I just,
You know, so the
having
negative
brain
is down,
farts.
and you did that, and oh no.
all right, there we go. So for this one, I'll actually write the answer down, like what our conclusion would be. Our original function is concave up. Let's see, it's only concave up between pi over 6 and 5 pi over 6. Right, that's where it's concave up, just here, between the two critical numbers. The original function is concave down at what, 0 to pi over 6. And then union that with 5 pi over 6 to, well, doesn't it just stay concave down this whole time?
Yeah, it seems like it.
Yeah, you can, and this number is in the domain, so we can use it. So this should just go out to 2 pi. Oh, do we have any inflection points? Do we have any points where we have a change in concavity? Where we go from either down to up or down or up to down?
5 or 6 and 5 pi over 6.
Right here, pi over 6, we go from down to up. So we have an inflection point at f of pi over 6. And then we have another one at f of 5 pi over 6. Now, if you wanted to know the values of the function there, you could go get those. You don't need them. Okay, the inflection point, all you really need to know is where it happens.
When
But
we're
if you wanted
writing,
to know the y, if you want to know the y value, you just plug those into the original function. Original, which is 36 minutes ago is when I wrote the original one down. Okay, what now, Hunter? Did you have a question?
I was asking, when we're writing the concavity, since 0 and 2 pi are included in the domain, would it be brackets or parentheses?
Either one, either one.
Okay.
Both would be correct. And it just has to do with the fact that you can't talk about increasing or decreasing or concave up or concave down without talking about 2 points compared to one another. And so it makes no sense to talk about something being increasing at a single point. Increasing, you have to have something to compare it to. So we just leave it off and it's fine.
All right. Just want to make sure.
Okay, whew, that was fun. So I'm going to graph this real quick, okay? The original function was cosine squared x minus 2 sine x. Is that what it was? Yeah, minus 2 sine x. And I'm only going to graph it on the interval 0 less than or equal to x less than or equal to 2 pi. All right, there it is. Now I'm going to change the scale here so that we're looking at this on increments of pi over 4. Yeah, pi over 4. Let's go pi over 6, pi over 12, 6. Oh, 6. Let me try 6 again. I was hoping this would change. Okay, it's not changing for me, but that's okay. All right, so here we go. Here's our graph. Uh-oh. Uh-oh. It's not letting me grab this. There it is. All right, on our first derivative, right? Here was our information off the first derivative. We said from 0 to pi over 2, we should be expecting to see it go down. So that's happening right here. It's going down, right? Right, like this. Between 0 and pi over 2. And then we should be expecting it to go up between pi over 2 and 3 pi over 2. So here's 3 pi over 2 right here. And you can see, I think you can see that it's going up here, right? Up like this. And then it gets here. That's where we had a local minimum here. We have a local maximum here. And then to the right of 3 pi over 2, it starts going down, right? That's what the first derivative told us. So everything matches up. Then we did our second derivative. And we did a little table for that. And here's what it said. To the left of pi over 6, we should be looking at something that's concave down. So here's pi over 6. So at this point right here, this is part of a frown, right? There's a little sad face over here. It's part of a frown. This part actually is not part of it, but it's I guess the right side of a frown. And then between pi over 6 and 5 pi over 6, that's between here and here, it looks like a smile. And it stops right there. And at that point, we go back to being a frown, and we should be a frown the rest of the way, which we are. Before computers, before calculators, this is how human beings graphed functions. Because you didn't have Desmos, right? You couldn't just go type it in. You had to figure out the shapes of these graphs by hand. And so the first and second derivatives helped us get very accurate pictures. I mean, we can't sit there and plot every single point, right? We're not computers. We don't work that way. We can't work that fast. So what we can do is we can say, oh, between here and here it goes down, between here and here it goes up, oh, between here and here it's shaped like this, and between here and here it's shaped like that. And then we can draw a pretty good picture. All right. I think it's somewhat obsolete at this point because we have computers. Graphing anything by hand is almost torture. But I think without doing this, you don't really understand like what the first and second derivative is giving you, right? The first derivative is telling you something is going up, the graph's going up, second derivative or down, and then the second is about that shape, right? That inflection that we talked about. All right, wow, we're like
So-
halfway through class almost.
Quick
It's crazy.
question, just before we
Yeah.
move on too far. So with Desmos, how do you put in a square root?
Type SQRT.
SQRT? Gotcha.
Yeah.
Because
Yeah.
I've tried to use it a few times and I can't get square roots into it. So
You should just be able to type SQRT and it'll throw a square root in there.
sweet, thanks.
Yeah, and I think if you write EXP, no, it doesn't do X. Okay.
No,
I
I know
haven't learned-
there's a little up arrow on there that gets the exponent that I was using.
Yeah, just there's all these different like syntax things for Desmos. I haven't learned them all, but you know. All right. Wow. So this is the issue with this section, right? Is that as much as I want to show you how to do these problems, we just don't have time for me to show you enough variety of problems. I mean, we actually need like what, 40 minutes to do one problem. So I can only show you like one or two. And then when you go do the homework, you're going to see stuff you haven't seen. I just can't cover enough of it. Does that make sense?
Oh yeah, no.
So it's
stuff is
really,
insane.
that's where it's like all these things are going to be stirred up, right? Pre-cal is going to be coming up and algebra. So I had picked a couple of problems before class that I wanted to look at that I thought had a good, these aren't trig, but these are two functions that I thought would be good to mess with, just so you could see some of the algebra.
Are
What do
we
you
going to
say?
have to graph a function by hand on the final?
I'm not going to ask you to graph a function by hand. I'm not going to. Now
That's the best
I'm
news I've heard all
probably-
day.
I'm probably going to be sitting in front of some jury of math. When I go to math hell at the end of my life, right? When I'm sitting there in purgatory and they're like reviewing my math history, you know, they're probably going to tell me, remember that, you know, semester that you stopped asking your students to graph functions in Cal 1? You're sentenced to an additional 100 years and whatever, you know, like, I think that the classic thinking here is that all Cal 1 students should learn how to graph functions by hand. Okay. What I've done is I've given you the tools to do it. Okay. Like all you would have to do at this point is take your critical numbers, plug those into your original function, and you would actually get dots. And then what you do is you connect all these dots together with what you know. So you would, you know, go down, then up, and then make it shaped like a frown or a smile. And yeah, I have to make choices. Where do we cut things out? And I think that's I'm comfortable with it.
Yeah. To be honest, as much as this is a lot more work, I feel like when it actually came down, when it would actually come down to writing down a graph itself, it would be easier than figuring out the points with any of the older methods that I would have learned, you know, because
Yeah.
you have so many points after you do all of that, you know, like
What's more important to me is that we learn how to do optimization problems, which are the word problems. Because what will happen is we'll take a real world situation, we'll turn it into a function. And then if we can graph that function and find its highest and lowest points, then we have everything we need. And so you really, to find highest and lowest points, you only need the first derivative. You don't need the second derivative to find highest and lowest points, just the first. So that to us is the more powerful, more useful thing. All right, so before I get into this one, because it's going to take us a while to do this one, tell you a quick story. It will only take 2 minutes. So there's a colleague of mine, I wouldn't say colleague, we were in school together, and we were just having like really math dork conversations, you know, like just conversations that only math nerds would have. And it was right around Valentine's Day, right? And this guy, this friend of mine, his girlfriend was also in like a math major. So they were a couple, they were both math majors. And he said, he's such an idiot. He said that he was going to tell his girlfriend that if he were to graph his love for her, right, that the derivative would always be positive. That's what he told me, right? So he's like, he said, if you were to, I'm going to tell, he's like, I'm going to tell my girlfriend that if I were to graph the amount of love he has for her as a function over time, that this love function that he has, f, that the derivative would always be positive. Right? So I was like, okay, that's great. She's going to break up with you though. And he's like, why is she going to break up with me? I said, well, because that's not necessarily a good thing. So what was he trying to say here? That if you were to look at this graph, what would it be doing?
Be like an exponential function going down, but getting close to zero, wouldn't it?
Well, no, because the derivative is
Right.
positive, right? Derivative positive
it's
means
going up?
It's going to constantly be going up.
yeah, it's going to go up. So this is what he meant to say, right? Is that this is what he was going to be romantic and tell his girlfriend, oh, the derivative of my love is always positive, right?
That's
Which
mega
means it
corny.
goes up, right? So, but I said to him, that's not enough, okay? Because you can have this happen. You can have a horizontal asymptote, and you can have a function that increases to that horizontal asymptote and continues to increase forever, but never reaches that point. Does that make sense? That is possible. And this function right here would have a derivative that's always positive.
So like marriage.
Exactly. This is more realistic, I guess. Shut my wife is right over there. Okay. So look, so I said, you know what?
I'm joking,
It's
I'm
okay.
joking.
We can recover this. We can recover this. You just need to add one thing onto it. You can say the derivative of your love is positive, but add one more condition. What condition? What's the difference between this graph and this one?
The second derivative is positive.
Second derivative. The second derivative needs to be positive. Because see, if your second derivative is positive, then you're concave up. And that means you can't flatten out. See, look, this is concave down. You see it's a frown? If you're going to increase and at the same time have to flatten out, you have to be concave down. But if you want it to increase and keep going up and not ever get stopped by anything, then you got to make it concave up. So I just said, real simple, man, just add the second derivative as positive, then you're in business. She's gonna like that. Is that ridiculous or what? This is a true conversation. I can remember it. I remember exactly, I was sitting on my desk, he was drawing it on a board, and I was like, dude, second derivative needs to be positive, man. So that, yeah. So, but I tell the story so you understand, like, the first derivative tells you a lot. The second derivative also tells you something, right? There's this relationship between the two. All right, so you're free. I know we're quite a ways away from Valentine's Day, but I will allow you to steal that if you'd like. If you want to put that in a card or something, that's cool with me. Everyone's shaking their heads.
I'm fine with the
Going on?
first derivative.
What did
going
his
on?
girlfriend say?
Yeah, how quickly did she break up after him after he told her?
Yeah,
Yeah, I
what was the
know, right?
result?
She dumped him right away.
All right.
Okay, all right, here we go. So for this function, I want us to do both, like everything. I want us to do increase, decrease, concave up, concave down, all that same business. So why don't you take 5 minutes and see how much of the derivatives you can get. So when you get the derivatives, you're going to have to try and clean them up a little bit. So see what happens. Go find the first and second derivative. I'm going to be writing these derivatives out while you're working on those. Y'all ready to talk about this first derivative? Product rule, right? Derivative of the first one times the second plus now derivative of this. Derivative of the square root of something is 1/2 times the square root of that something. Then the derivative of what's inside, -2x. Then times x to finish off the product rule. That's what I've tested you on in the past on. And I've said, I'm happy if you can get it to that. But I said, one day you'll have to set it to 0. So now I'm going to start putting things together. So I put these two together. That gave me -2x squared. And then I canceled this 2 and that 2. And then I put the negative right here. And I put the x squared on top and just left the root on the bottom. So everyone good with these first 2 steps? Questions? Next step.
That's the part I have questions about.
Common denominator. So I have to multiply the top and bottom by 2 minus x squared. Because I'm going to try and force these into one fraction. So when I multiply the square root of 2 minus x squared on the bottom and the top, on the top, they're the same roots. So when I multiply them together, the roots go away. And I'm left with the 2 minus x squared that was underneath the root. And then it will have the same denominator as this one, so I can push these two together. And that's why this minus x squared joins on the numerator. And then the next step is just to put minus x squared with minus x squared to become minus 2x squared. That good?
Yep, that's also going to be easier to take the second derivative of.
That's kind of, there's two advantages to putting it together. One is that it'll be easier to set this equal to 0 than it would be to try and set this equal to 0. And the other thing is I need to take a derivative again. So let me go with the second derivative. And I'm going to have a nasty quotient rule here, right? There's my quotient. So here comes my quotient rule. Second derivative. Quotient rule says I take the derivative of the top, which would just be -4x, times the bottom, which is the square root of 2 minus x squared, minus, now the derivative of the bottom, which is a square root. So we've already done this. It's kind of ugly. It's 1/2 square roots of 2 minus x squared times -2x. That's the chain rule on the bottom. But all of that's multiplied times the top, which is 2 minus 2x squared. All of that divided by the bottom squared. That is it, right? It ain't pretty, but that's it. Questions on that quotient rule? Because I'm about to start cleaning it up. Any questions on it? Gone, gone. The negative and negative become a plus. This x distributes through. All right, so here's what I've got. -4x square root 2 minus x squared plus, because those two negatives become a plus, I have the x distributes through, so 2x minus 2x cubed over the square root of 2 minus x squared, but then all of that over 2 minus x squared, because I'm going to square the square root on the bottom. So that will kill off that. Still good? I have to set this equal to 0. So I do not want to do that right now. So I'm going to start again pushing everything together. So I'm going to try and put these two together first, which means I need to have a common denominator. So I'm going to multiply the top and bottom of this fraction by what?
The denominator.
The denominator, root 2 minus x squared on top, root 2 minus x squared on the bottom. And be careful, this is multiplied, so that's not a subtraction there. This is going to be multiplied. So when I do that, I'm going to multiply those two roots together, which will make the roots go away. And so I'll have the -4x. Those two together give me, in parentheses, 2 minus x squared. Then I have the other one's numerator, 2x minus 2x cubed, all over their common denominator, root 2 minus x squared, all of this over 2 minus x squared. Are we having fun yet?
It's interesting.
Equals. All right. Distribute. -8x plus 4x cubed plus 2x minus 2x cubed over 2 minus x squared to the 3/2. Okay, what the hell just happened? What happened? Here's what happened. I looked at this as being over 1, which means I have a fraction on top of a fraction. And so I multiplied by the reciprocal, like that, instead of this. And then this is 2 minus x squared to the first power. And this is 2 minus x to what power? 2 minus x squared to what power?
The half.
The half. And so I put the two together to create a 2 minus x squared to the 3/2. So I'm really just rewriting this one as this to the half. And then I'm multiplying those two together, which means you add their exponents, which gives you 3/2. (2x cubed minus 6x over 2 minus x squared to the 3/2. That's a pretty clean second derivative now. I picked this problem before class because I thought it had an appropriate level of algebra that would make you go, oh, I better go practice. Like,
There's
I
a
better
bunch
go
of little
practice.
details.
Yeah, there's a
That's
lot of
awesome.
little things here. All right. All right, we've got the first and second derivative. Wonderful. Okay, now let's go back to the first derivative and let's go and get our critical numbers. Anybody feeling ill yet?
No.
All right, so I want to know two things, right? I want to know, first of all, when the derivative is 0, and then I want to know when the derivative doesn't exist, right? All right, so let me look at my derivative. The derivative is a fraction, right? And we said last time that the only time a fraction can be 0 is if the top is 0. So I'm going to just set the numerator equal to 0. I'm going to move the negative 2x squared to the other side. I'm going to divide by 2. And I'm going to take the square root. So I should get plus or minus 1. 2 answers. Now I need to check to see if these numbers are allowed, right? Are these numbers allowed? Because it could be that these numbers are not allowed. So we got to go back to the original function. And let me put it right here. There's our original function. Does our original function have any domain restrictions? Is there any, can we, well, let's just look at it. Can we plug 1 into this? Would it work?
Yeah, it should work fine.
1 should work. -1, -1 squared is 1. This should work also. Both
Yeah, it
of
should
these
also
are
work.
within the domain. We're okay. Now, what about where the derivative doesn't exist? So look at your derivative. Is there any problems you would ever have here? Maybe, right? Like, look, you have a square root. So you better promise me that this right here is never negative, and you better promise me it's never 0, because if it's 0, you have division by 0. So for
X
this,
has to be greater than 0.
we need
Uh,
what to be what? We need
the-
2 minus x squared to be greater than
Yeah.
0, don't we? In order for this to work. And this is a quadratic inequality. This is a quadratic inequality, which you study in college algebra. And there's a method to solve a quadratic inequality. And it is not this. It is not you move the x squared over and then take the square root of both sides. That is not the way you solve a quadratic inequality. That's how you get yourself into trouble. So the way to solve a quadratic inequality is to do this. You take it and you first make it an equation. So if you need to put a star here, quadratic inequality, if you need to go back and review how to solve quadratic inequalities, go do it. But I'm just going to show the method. You go through, you make it an equation first, you solve the equation. So you will get 2 answers here. You take the square root of both sides, you get plus or minus √2. What you do next, though, is the critical thing. You're supposed to take a look at what happens to the left and to the right of these numbers. So this is not me checking to see where something goes up or down. I'm in a completely different world right now. Do y'all understand? I'm in college algebra right now doing a quadratic inequality. I'm not doing anything over here with up, down, any of that, concavity. I'm not doing any of that. I'm doing, how do you solve a quadratic inequality? So I set change the inequality to an equal. I solve it, and then I pick little test points and I plug those into the inequality and see if they work. So let me pick a number over here like -4, number in here like 0, and a number here like 4. And I'm just going to check them in here and see if they work. So -4, if I plug it in here, does it work? If I take -4 and square it and then subtract it from 2, is that bigger than 0?
No.
No, right? So this doesn't work. If I plug 0 in here, it does work. And if I plug 4 in there, it doesn't work. Which means the only numbers you're allowed to have that make sense are things between, or x must be between negative root 2 and positive root 2. Got to be between here and here.
I have a real quick question.
Yes.
So whenever, just like for notation, can we do like f of numbers, like for example, 1, -4, 0, and 4, and put commas in between them and then close the parentheses, like as notation to indicate that we're plugging those numbers into the function? Or does that mean something else?
Can you do what?
So like, yeah, you have like f of x or f of any number. For this instance, it was -4, 0, and 4. Can we put
Mhm.
commas in between there? So f of -4, comma 0, comma 4, and just to like indicate that we're plugging those numbers in. Right, just
This?
like that.
In that, you're asking, is that notation appropriate to mean that you're going to be plugging in -4, then 0, then 4?
Yes, yeah.
No.
Okay.
Only because in Cal 3, that would actually mean something completely different. So anytime we want to say we're going to do it, we would have to do, okay, this. That's what you would have to do, like each one individually.
Okay, got it.
Yeah.
Appreciate it.
Yep. All right, so I got to get to my number line here. My number line, I have the critical numbers 1 and -1, which we said are good. You could plug those in, right? And then over here, we discovered that, you know what? We can only go out to the root 2 and only over this way, -√2. Basically, anything over here doesn't exist and doesn't exist because that's going to cause problems with the domain of the original function, right? 2 minus x squared has to be bigger than 0, which is basically what we were saying right here. So we got to pick test points here, here, and here, but anything outside of that doesn't make sense. So I got to pick something here, here, here. So 0. Unfortunately, you're gonna have to pick a decimal because this is 1 and this is like 1.414 or something. So I'm just gonna pick 1.2. And then over here, I'm gonna pick -1.2. And I'm gonna plug those in to
First derivative?
the first derivative, right? So we want to know what f prime of -1.2 is, f prime of 0, f prime of 1.2. And yeah, this is your derivative. Plug it in. Copy, paste. I can do a shortcut here. Because here's what I can tell you. And I think hopefully you'll agree with this. Do y'all agree that the denominator is always positive? Think about why. The only way this is ever going to make sense is if you plug a number in here that 2 minus that number has to be positive, right? If you plug in something that is like, if you try and plug in 4, this isn't going to work. We know we're looking between -√2 and √2. We know that the numbers we plug in here should work. So we know that we're going to get a positive underneath the root, and the square root of a positive number is positive. So I know that the bottom's positive. The numerator is the only thing that really matters. So let me just figure out what's happening here. Let me go with the easiest one first. If you plug in 0, right? This one, 0 for x, you get a positive on top. So I know that this can be positive. I also know that whatever I get for 1.2, it's the same as -1.2. These are going to give you the same answers because we're just going to square it. That's the first thing we're going to do. So if you can check it for yourself, but if you plug in 1.2 and square it, multiply by 2, subtract that from 2, you should get a negative number. You can get your calculator if you need to, whatever. You get a negative number here, you get a negative number here. So what's this tell us? It says that over here in this region, the function's going down, here the function's going up, and here the function's going down. So we should expect to see down, up, down. I'll come back to that. I need my second derivative. Questions? I need to know when my second derivative is 0. I need to know when my second derivative doesn't exist. Setting it equal to 0, just set the top to 0. Luckily for us, we can factor out a 2x, which leaves us with x squared minus 3 equals 0. Right? We can set each of these equal to 0. We get 0. And then here, if we set that to 0, move the 3 over, we should get 2 answers plus or minus root 3. Understand? Are we going to keep these? Is 0 in the domain of this function? Remember what we were talking about here. This 2 minus x squared, this thing right here better be positive, right? This is the original function. This thing better be positive, which means we better stay between negative root 2 and positive root 2. So 0's in there, right? 0's in there?
Yeah, root 3 is larger than root 2 though.
Yeah, root 3 and negative root 3, those are outside that window.
It's like 1.7 in a
Yeah,
huge
so they
freaking string of
won't
numbers.
work, right? These won't work. Does everyone agree? You have to see that. If you don't see it, you're going to wind up wasting time drawing a number line, and you're going to have these critical numbers that aren't even part of your picture. You're just going to be adding more stress onto your already stressful life. Okay, so we want to eliminate those, get them out of there. Now, where the derivative doesn't exist is the same question we had before, because you see this 2 minus x squared underneath? That right there is really the square root of 2 minus x squared, that whole thing cubed. That's what that really means, right? To raise it to the 3 halves is the same as taking the square root and cubing it. So whatever the problems we had with the previous one, right? The previous derivative had that same issue. We have that same issue here. We need to make sure that that stays positive. And so we have the same sort of story as we had with this.
Shouldn't it be the same set of numbers too?
It's the same set of numbers.
Because
Exactly.
the cube won't affect your negative sign.
That's right.
or
It
a
won't
zero.
have no impact. Which means that when I go to draw my critical number, I only have one critical number, 0. And then here we have negative root 2, and here we have positive root 2. We know that to the left of this, I can't look here and I can't look here. This is good. This is good. I'm happy about this. That means I only have one test point on each side. I'm going to go with -1 and +1. Those are going into the second derivative. I'm going to try and get this all on one page. So the second derivative, I got to plug in -1, and the second derivative, I've got to plug in +1. And here's my second derivative. If you plug in -1 on the top, you get -1 cubed. It's -1 times 2. So you get -2. And then when you do -6 times -1, you get +6. And on the bottom, I can tell you that the bottom is positive for the same reason as the first derivative. You're going to have basically this over here. You know that this square root thing is going to be positive. Has to be, because what's underneath has to be positive. So square root of that's positive. You cube it, it's still positive. So I know the denominator is positive. The top's positive. We get positive there. Now, if I plug in +1, I get 2 take away 6 over a positive number. And this is going to give me a negative number. That tells me the original function's concave up here. And then the original function here is concave down.
Shouldn't that be inverted?
What?
Your concave up and your concave down?
What do you mean inverted? I'm not sure what you mean.
Shouldn't it be concave down on the left and concave up on the right?
At -1.
Oh, wait, nope, never mind.
Yeah, okay.
I'm misreading.
-1, we had a positive, so concave up. At 1, we had a negative, concave down. Okay, we good? Or, I mean, I don't know if you're good, but you there?
Not for a second there, apparently.
So here's what I'm doing, because I told you I'm not going to have you graph these by hand, all right? I'm going to show you how you would do it, but I'm not going to have you do this, all right, on a test. What I'm going to be looking for is that you can do this. You can create this table, and you can create this table right here. If you can do that, I think I'm happy, you're happy. Well, I don't know if you're happy, but you'll be happier than if I asked you to graph it. So here's the way you would graph it, okay? I'm going to show you this. Again, this is for your own just enjoyment. So what I would do to graph this is this. I would start with the number line. -√2 to √2 is I know where this is defined, right? Now, from the first derivative, I had this picture, right? That's from the first derivative. I had an important point, -1 and 1. So what I would do is on this number line, I would put my -1 and I put 1. And then from the second derivative, I had the important point was 0. So I'm going to put that here, 0. All right. Then what I would do is this. I would draw, I'm going to make a table. Just follow me through with this, okay? And for this table, I'm going to have 3 rows, okay? 3 rows. How many columns you have depends on how many critical numbers you had with your first and second derivative. All right, so if you had a bunch, you would have a bunch of columns, but you'll always put 3 rows. Now what I'm going to do is I'm going to go back to my first derivative, and I'm going to look at what's happening with my first derivative. Then I'm going to be looking at what happens with my second derivative. So my first derivative goes down, up, and down, and it happens at -1 and 1. Right, so down to -1 and then up between here and then down. Watch the way I do this. On the left side, I'm going to put f prime, and then now I'm going to say it went down. It's going down over here, right? My function's going down. And then it goes up, and it goes, how far does it go up until I get to where?
Till you get to the 1 again.
So I get to 1, right? From -1 all the way to 1, I should be going up. And then once I get to 1, it goes back down again. Got it? Now the second row is going to be the second derivative. So now I go back to this here, and I was concave up all the way from -√2 to 0, and then concave down from 0 on. So watch the way I do this. It's concave up, right? All the way till I get to 0. So it's going to be concave up, then concave down, concave down. Understand that? My last row is what the final function has to look like then. So here's the way I want you to think about this. Think about this first column here. What would it look like if you had a smile but had to be going down? You could only be which side of the smile. So here's a smile, right? If we look at the smile right down the middle, on the left side of a smile, you're decreasing. On the right side of the smile, you're increasing, right? Yes?
Left side.
So what? Left side. So we know that over here in this region, it must look like the left side. Oh, that's a little too much. It must look like the left side of the smile. And then this region in here, you must be going up on a smile, which means it must look like the right side. But then you have to switch and start going up a frown. So if you're going up a frown, which side are you on?
The left side.
The left side, right? The left side is up and frowning. So it has to look like this. And then here you have to go down and be on a frown, which means you have to look like the right side. So what I'm doing is I'm using these two pieces of information to deduce what this picture has to look like. I mean, does that make sense to you? I'm using that, I'm up a smile. Oh, I've got to be the right side only. Can't be on the left side of a smile because then you're going down. That's the first, this is, remember I told you the Bobby method? Remember that? I told you about the Bobby method last class. This is the Bobby method, okay? Textbooks will use something completely different. They'll use the sign chart. Let me see, I think I have the book open right here. I thought I did. Logged me out. Oh, well, maybe I'll show you later. Okay, so this is the first thing, right? It's my first step, is to draw that. Now what I do is directly below this, I'm ready to draw my graph. And so what I'm doing is, since this is 0, I'm going to put the y-axis, then I'm going to put the x-axis, and then I put 0 here, I'm going to put 1 here, and I'm going to put √2 here. I'm going to put -1 here, I'm going to put -2 here. All right. I'm going to take each of these points and plug each one into the original function now. So I want to know what's happening at -√2 in the original function, or
I
yeah, this
think
is the
you put
original
-2
function, which is
instead of
y.
-√2.
Pardon me? Yeah, I forgot to put the root, sorry. Then at -1, then at 0, then at 1, then at √2. Plug all these in. So where's my original function? Way back here somewhere. That was it. Here we go. Okay, so let's plug in, let's do the easy one first. 0. Can I plug in 0, please? 0 kills everything. This should just get me 0, right? How about, let's plug in 1. We plug in 1, I get 1 times, let's see, this 1 squared, so 2 minus 1 is 1. So I get √1, so 1 times √1, which should give me
1.
And let me try √2. So if I plug in √2 here, it's √2 times √2 minus, wait a minute, what's √2 squared? What's √2 squared?
2.
2.
Okay, and then the 2 minus 2 is?
0.
0. That kills that off. It goes to 0. If I plug in -1, let's see what happens. If I plug in -1 here, -1, and then -1 squared is 1. 2 minus 1 is 1. √1 is 1. So that should give me -1. And then if you plug in -√2 here, you'll also get a 0. Y'all trust me on this? I'm going to plot my points. I'm ready for my graph. Okay. I'm ready for my graph. When I go to -√2, I should be at 0.
Wait, how do you get 0 with -√2?
Because when you square right here, if you take -√2 and you square it, it becomes +2.
Oh, okay.
Because
I
you
was-
square the negative also, right?
I was doing the math in my head with the negative outside.
Yeah, this negative stays in there, then it will get killed off with that minus there, or 2 take away that 2. So at -√2, we're at 0. At -1, we're at -1. So I'm just going to go say, let's just say that this is -1 right here. At 0, I'm at 0. At 1, I'm at 1. Hold on, that was a little bit off. And then at √2, I'm at 0. Got it? I've got all my points now. Now what I'm going to do is I'm going to kind of imagine like we're kind of transposing what we found out about this region, right? What do we know about this region? We've got to look like the left side of a smile. So I'm going to connect these 2 red dots with the left side of a smile. And then I've got to connect this dot to this dot, and it's got to look like the right side of a smile. And then I'm going to connect this dot to this dot, but it's got to look like the left side of a frown. And then I got to connect here to here. It's got to be the right side of a frown. Voila. Voila.
Well,
All right, let's see if Desmos has any problems with it. X square root 2 minus x squared. I think that was a little bit faster.
just a little bit faster.
Just a little bit faster.
So in summary, we spent an entire hour and 40 minutes doing 2 problems.
Yeah, 2 problems. Yeah.
This is my favorite kind of math. The one where you give us 3 homework problems and it takes longer than the other section where you gave us 20.
Yeah, there's so much work here in these sections, but I mean, look, I mean, that's what we did, right? I mean, our graph is pretty good. I mean, that we have a pretty good representation of that. I don't know. Yeah, theirs is better, but ours isn't bad. Again, imagining that you don't have a computer, right? This is why I'm saying I'm not going to test you on graphing this, because really at the end of the day, if anybody ever wants you to graph something by hand, you need to probably go find another job, because that's not fun, right?
Seriously though.
Yeah. All right. And you know what's so great about the technology, and I showed you all this last time, is that you know, when you graph it, it already found the max and min. Like you can just hover over it. It tells you the points, you know, it's awesome. All right. Well, we have 10 minutes, which isn't a whole lot of time, and we definitely can't do another problem. So I had another one here for you, right? I had another one here for you. Why don't we just, in 10 minutes, why don't we get the first and second derivatives of these? We'll do it together as a group, okay? I'm gonna get the first and second derivatives here. And let's work on cleaning it up, all right? So here's my graph, here's my function. I want the first derivative. The first derivative actually doesn't look that bad, does it? I mean, these are 2 terms. You can just take derivative of each one, right? One by one. So 1 minus, just power rule on that one. So bring the 1/3 in front, which should just give you x, and then subtract 1 from the top. You should just get x negative 2/3. By the way, this is the same as x minus 3 cube roots of x, isn't it? The same thing. And as far as the domain of that function, it should be everything, because you can take the cube root of any number. You just can't take the square root of any number. So there's no domain problems here for the original function. There's my first derivative. Hey, look, that was pretty nice. Let's go ahead and crank the second one out. The derivative of, this is, hold on. I'm muting everyone because I hear something in the background. It's kind of distracting. So I took my first derivative. There it is. Now my second derivative, good. Derivative of 1 is 0. And then derivative of this, power rule again. So I get a 2/3 that comes out. I've got to subtract 1 from this. So that gives me negative 5/3. Would you all agree those first 2 derivatives were pretty nice as far as just executing what they were? We still have to clean them
Yeah,
up.
that was pretty simple.
They're nice, no quotient rule or product rule or any of that. So let me start working on these to kind of see what they look like. This really is 1 minus 1 over x to the 2/3. That's what that really is, right? I'm gonna need to set this equal to 0. So since I need to set it equal to 0, what I'm going to do is my standard kind of technique, which is to get a common denominator between these two, which means I'm going to put an x to the 2/3 on top and an x to the 2/3 on the bottom of this 1. And that would give me an x to the 2/3 on top minus the other one's numerator all over the common denominator. And I think that that is something that I feel willing to work with. Because if I have to set that equal to 0, I can just set the top to 0. If I need to look at where it's undefined, I can see the denominator. Got it? Let's do the same thing on the other one. Let's just clean it up. This is, well, that's even better. It's 2 over 3x to the 5/3. That's all that is. Just drop the x to the 5/3 down. There's nothing more to do. I mean, that's a fraction, right? We still have time. I think we can set.
If we set that second derivative to 0, what would even
no
happen?
solution.
Yeah.
Yeah. So we have some interesting stuff here. Let's do this first derivative. Okay, let's do that first one. Let's figure out where it's 0. Was this y? Yeah. So where's the derivative 0? Where's the derivative not exist? All right, so where is it 0? We take the numerator, we set it equal to 0, which means we take the 1 to the other side. What do you do here? How do you solve for x?
That's x. That's the cube root of x squared, right?
That is the cube root of x squared.
So we could cube 1 and then take the square root of it, right?
We could do that. So this is the cube root of x squared equals 1. So you could cube both sides first if you wanted to.
Yeah. Which
Cube both sides,
it's going to be 1.
which will still give you 1 on the right.
Yeah. And then the square root would still also be 1.
Square root would give you plus or minus 1.
Yes.
So when we do the square root now, you do plus or minus. Everyone understand that? You need to cube both sides. The reason I like that method is because I know some of you have been taught to do this, and this is okay. Raise both sides to the 3/2. And this will have the same effect. This right here, when you multiply, you get an x to the first power. And then on this side, well, you'd say 1 to any power is equal to 1. The problem with that is you miss the negative. You have to make sure that if you're raising both sides to the same power, if the fractional power has an even number in the denominator, you're going to have to do a plus or minus. So that's why I like this. This was, I think, better than this. All right, I'm going to keep rolling. Where's the derivative? Oh, are these in the domain of the original function? Well, the domain was everything, right? So we're good.
Shouldn't be any problems.
Okay, where does the derivative not exist? So you look at the derivative, here it is. Oh, look at the bottom. What if it's 0?
Yeah, at x equals 0, it won't exist.
We want to make sure that this can't be 0, but that can happen at x equals 0, and x equals 0 is in the domain. So we have 3 critical numbers. They are 0, 1, -1. We're going to need 4 test points. I will leave that to you. All right, you can enjoy the rest of that. I want to look at the second derivative. So I'm just going to put here ... You can go have fun with that. The second one, the second derivative. Whoa, that was really big. I want to know when the second derivative is 0 and where the second derivative doesn't exist. All right, where's the second derivative 0? Well, you take the numerator and set it equal to 0, right? That's never happening, right? 2 is never 0. So you have no solutions there. And then where it doesn't exist, well, there is a problem. You could get division by 0, right? If that 3x to the 5/3 equals 0, you have a problem. You don't want that. So x equals 0 is a critical number. So you draw a number line. Here's 0. and you pick your test points and go get your concavity.
That's a weird one. I don't think I've seen one where I had a does not exist, and then
Not
there
a-
isn't a point where it equals 0.
Yeah, and I'm glad you brought that up because there are problems, okay? Pay close attention. There are problems where you will have that both of these don't have a solution. Okay? So
That means
if that happens, if you have something where you have no solution, then that means when you go to draw and then do your test points, you don't have that critical number, right? You don't have a critical number. So what you do is you pick any point as your test point and just plug it in. And that means you'll either get concave up or down. And so that means that it's always concave down or always concave up.
Oh, okay. So that means that there is no point of it changing.
That's right. There is no point where it
Gotcha.
changes. Yep.
I'm
A
hearing
good
is you plug
example-
in 0 every day.
Yeah, here's a good example. Watch, I'll show you because we got 2 minutes. If you take y equals e to the x, okay, what's the derivative of that? Well, itself, right? What's the second derivative of that? Well, itself, right? So if I ask you to take the first derivative, set it equal to 0, or tell me where the first derivative does not exist, well, the first derivative is e to the x. That's never 0, right? That's not ever going to happen. So you have no solutions here. And then over here, does it ever not exist? Does the derivative ever not exist? No, e is always defined, e to the x always defined, right? So you have no solutions here. Does that make sense? What's happening? Like what? So what I do is I go, okay, well, what's going on here? I don't have anything to put here, right? I don't have anything to put here. So I just pick any point I want. How about 0? And test it. Let me plug that into the derivative. So if I plug 0 into this, you get e to the 0. What's e to the 0? Well, positive, right?
Yeah.
So that tells me that my function is going up here. And not only there, everywhere, right? It's always going up. And then if you do the same thing for the second derivative, it's the exact same thing because it's the same function. So you get no solutions for this. You go to your number line, you say, what do I put in here? I don't know, just plug in 0. And what did we say? It was positive, right? So your second derivative is positive, which means your function is what here?
Concave up.
Concave up. And we all know that what e to the x looks like, right? E to the x looks like this. It is always increasing and it is always concave up. All right, everyone, it's 2:40. So what I think you should do for homework is let me tell you what to look at. I mean, really it is, you know, whatever is in this section. See, we're still in this section, so let me do this. Give me about 30 minutes. I'll send you all an email with the homework problems I think you should look at. It's going to be a lot though, but I recommend you try and get as much of this done and understood and get through all the algebra this weekend because, you know, next week's Thanksgiving, right? So we're all going to get buried in, you know, other things, and you don't want to be, well, you probably are going to need to be doing math over Thanksgiving weekend, but you know, you don't want it to be everything. Try and get as much of this down as you can now. All right, everyone, have a great weekend. Thank you again, everyone, for all of your understanding with the last week or so. You know, I know it's been, I don't think it's impacted you too much other than last week, but I appreciate everyone being understanding. So have a great weekend. I'll send something out soon.
Have a good one.
Thank you, sir.
Have a good day.